All right, good evening, class. So let's get started. I'm the lecturer for the segment C, about control optimization. So we will spend 2 weeks on this. So first of all, let's be very clear about why do we need optimization for control problem. Control specifications often have multiple objectives which may conflict. For example, let's say if you want to reduce the steady-state error, you may want to increase the gain of the controller, but increase the gain will lead to a higher energy cost. So here is just an illustration of the compromise between the control effort and the settling time. As you know, in many cases, that let's say you want to make it very fast, right? You want to make it very fast, which means the settling time is very short. It will require a huge control effort. But of course, and then of course it will be very expensive. But then you say, okay, I don't care about the settling time. The settling time, can be very long. Then yes, in that case, the energy consumption will be low. But if you make the settling time too long, that may not satisfy the performance requirement. For example, if you design air conditioning, right? Air conditioning, what is the settling time you prefer? Okay, you can design it to be very fast, like 1 second. Yes, indeed you can do that, but if you do that, the energy consumption very, very high, right? You have to have a very powerful engine to do that. But let's say, okay, normally you will say, okay, I settling time means that, okay, I set the reference, my desired temperature, let's say at the 25 degree, right? How long does it take for the room temperature to settle down to that value? And as a human being, we would say, okay, probably 1 minute, right? You would feel comfortable, 1 minute, I get the right temperature, right? That one, you say, okay, performance is okay, and then the energy consumption is also all right. But then you say, okay, actually, I want to save the energy. You say, if you will say, I want to make the settling time to be 1 hour, right? But 1 hour is too long, right? It takes 1 hour to settle down. Of course, then that will save a lot of cost. But meanwhile, you will lose the comfortability, right? So the optimization is about, you try to achieve the best trade-off among all the desired objectives. We'll make balance between the normally, right, the converging speed, the settling time, and the control efforts. Look, right, always there is no free lunch, right? If you want to do something, you have to, it will cost you something. Then how do we achieve the best goal? Okay, for this course, since we only have 2 lectures, but I want to, give you a sense about what are the popular approaches to solve the optimization problem. So therefore, instead of going deep into one approach, I'm going to discuss 2 approaches. The first one is today's subject is we call the calculus of variations, in which the minimum solution is regarded as a point in a function space. The second one is a dynamic programming approach, which will be introduced next week, in which the optimal policy, right, is computed at every state. Since we only have 2 classes, so I'm going to only discuss the solutions to the scalar case. Just as a starting point, if you are interested, of course, you can get a textbook on, there are books on both subjects. For the CA1, for my part, of course, there is a continuous assessment. There are 4 problems you are going to solve, right? The 4 problems are related to the calculus variations and dynamic programming. And if a student chooses to do a project with me, right, which means okay, you are doing the EE5110, you also know, and you need to talk to me about the requirement about the project. All right, so why do we need optimal control, right? When you are undergraduate, this is kind of a very common block diagram you have encountered when you learn the control engineering. This is what we call the unity feedback control system. There is a system you want to improve the performance, and then you build a controller for that. Let's say in the real world, if you are given a system, right, without a mathematical model, and you want to design a controller to improve its performance, what would you do first? Exactly, right. I mean, PID, you don't need a model, right? You try the model-free method, the PID controller should be attempted first. Actually, 90% of the controller used in industry actually are PID. It's very effective for simple problems. You don't need other advanced ones, okay? Definitely. But if, right, in some case, if the performance of the PID controller is not good enough, what would you do? PID doesn't work. Then pole placement. I said pole placement. Well, but if you do the pole placement, you need the model, right? So, which means, okay, I kind of use some model, of course. Right now, there are also some approaches called data-driven control, right? They don't need the model, they can do it. But that's not the subject today. So normally we need a model. So you are going to use a physical laws and identification techniques to build a model. Once a model is available, what's the simplest model-based controller you have learned in the past? What? Okay, linear system is not linear system is a course, right? It covers many things. The simplest model-based controller, of course, you are going to learn. You have learned that is a pole placement, right? Pole placement. You want to change the poles of the system to some desired ones. For example, the original system like this one is unstable, right? Unstable, but then you can change the poles by designing a feedback controller. But that one you need to know the model. So you can use the pole placement to make transfer function of the closed loop match some desired reference model. Okay, first, of course, you want to change the poles because feedback can change the poles. Let's say you want to design pole placement controller. When you design the pole placement controller, do you ever care about the size of the control signals? In the design procedure, are you required to do that? No, right? What you require, okay, I know the reference model, I just know the position of the poles, right? Desired position of the poles. So the objective of pole placement is try to place the poles of the closed loop to some desired ones, but we never ask the question if the control input can be supplied by the actuator or what the cost of the control is. In real control system design, should we care about the size of the control signals? Definitely, right? Definitely. In theory, if there is no control signals we computed, it can be produced. You can make the system to whatever you like, right? You can make the car run faster than the rocket. Yes, if you can have an engine, right, to produce so much power, which means because we assume that you have unlimited, right, unlimited size of the control input you can supply. But of course, in reality, we know we must be reasonable, right? We have to weigh the cost of undesirable performance of the system against the cost of control. This is one of the basic facts for control theory, right? We saw low free lunch. If you want to make it run faster, of course, right, the engine has to produce, right, a huge amount of power, which make it more expensive. Right? And of course, you want to save cost, you don't expect a high performance. It's like when you want to buy a handphone, right, smartphone. If you pay more, of course, you expect more functions. Yeah. All right. So therefore, we're going to take a look at how we're going to solve this problem. Okay, let's take a look at one example. Let's say the the single link robotic arm, right, or the reverted link pendulum, right. Let's say I want to make this one to move at some desired fashion. Then if you consider that pendulum example, after linearization around the equilibrium point, we say we are interested in this upright position. We know that is unstable one. Then we will have a model, right? This model is a linearized model. Then let's say with our objective, we want to bring the output, right, to 0, right, if there is a small deviation. Definitely we have to use the feedback because we know this system is unstable, right? If feedback control is used, which means that the input depends upon the output. So the input is a function on the output on the position and the speed. And let's say how we're going to choose the control action, right? So we want to choose the function or the control input in such a way that the position, right, and also the speed approach 0 reasonably fast without violating the condition that the magnitude must not be too large. Okay. I want to make it fast, but also the value should not be too large because, right, remember, if you want to make the position go to very fast to 0, but the speed will be large, right? So you have to have a kind of a balance. But when we look at this statement, let's say this is the requirement. We know, of course, this is not a mathematical statement. We want to, translate this requirement into some mathematical language, right? So how do we translate the requirement of a real-world application into mathematical language? That is the most important skills for engineers. Because as an engineer, if you go out and you want to do something, right? Normally, right? Let's say the upstairs or the boss tell you they will tell you the requirement in terms of some daily language, right? You want to, how to solve that? You have to, have the skills to translate that into a mathematical problem to solve. Okay, let's say how we're going to, do that for this particular problem. Okay, now this is a requirement, right? We want to, design a control law such that we want to make the position, the movement, and also the speed, right, small on average. Then we have to ask the question, right? How are we going to compute the average? Let's start with the simple ones. How do we compute the average for numbers? Let's say you have a set of numbers. How do you compute the average? Of course, this one is easier. So you learned that when you were, let's say, a middle school student, right? So this is straightforward for numbers. But we know that here we say, okay, on average, the output, right, the position actually is a function of time. So how do we take the average for the continuous variable, right? Let's say a function of time over the interval. Let's say from the starting point to t. The way, right, think about that. I mean, actually, it's also, you are going to take the average, but the average is over our interval, right? And also, the student already called out the answer, right? I mean, remember, right, the integration is about the summation, but we can just show it very easily. We say, okay, actually we take the average, but this time, right, you may take the sample values depends on how many samples you use, right? Let's say if you take n samples from this interval, you'll get this n, you take the average in this way. But let's say you take the samples for a small interval, right, delta, you divided those whole interval into a small segment. In that one, okay, you take the samples, then we multiply both sides by the delta. length of the small interval, right? You can say actually, essentially it is the same as this. I would take the average, but if you do it, you cut this duration into small intervals, right? And actually it is average. You can say, but on the top, this average, right? But you multiply by those small segment and you sum them up. That makes it into a integral. But of course, in the denominator, those n, you put all those segments together, you have those whole duration, which is t. Because from calculus we know, right, the integration is about the summation, right? So therefore, remember, integration, if we integrate something, actually it means that you are doing the average. You are doing the average about the function value. Okay? Is that clear? So, for this segment, for my part, it's a bit mathematical, but I want you to understand the basic idea behind the optimization approach. But also I want to just, don't just remember the formula. I want you to understand all the derivation details such that you know, okay, I hope after the class you say, I can also do it, right? You can also do it by yourself. So you try to follow all the steps involved. You have any questions, you can just interrupt me. Of course, I'm also asking you a lot of questions to help you to see how we can get there, okay? Okay, let's move on. All right, so let's say, therefore, we say, okay, we want to design the control laws, right? U equals, this is the feedback control, so that the quantity, the integral of this, because we want the position and also we want the speed, small on average. Okay, this is, we say, okay, actually, we want to make this integral minimum. Now you can say we have translated the requirement that the signals are small on average into some mathematical form. So that's the skill you need, right? When you say, I want to do something, what does that mean? You want to put it into a mathematical problem you want to solve. Okay, this is also the case for many engineering problems. You have to convert the problem, a practical problem, into a mathematical problem to solve. But then what about the input, right? In that formulation, we haven't considered the input. We didn't consider the cost of the control. Different types of control laws will require different amounts of effort. So how should we estimate this type of control? One way, of course, is, okay, I want the cost, the average cost to be small, right? So therefore you want to say average cost, right? Well, then we take the integral of u squared. If we add the two costs together, then we have a total cost. This cost is about the cost on the output. This cost is about the cost of the inputs. We put them together. Then the problem becomes, well, how do we choose the feedback control function or the control law such that the cost is minimized? But when we look at this question, now you can say, is this an optimization problem? We want to minimize something, right? We want to find out the smallest value. Of course, that is the optimization problem we're going to solve. All right, okay, let's say then, let's start from the beginning or what you have learned in the past. So it's about optimization. If you are given a function, a scalar function fx, right, is a continuous function and also a smooth function, you want to find out the maximum value or the minimum value. So where do we search? How do we search? You learned that in calculus, right? How do you find out the optimal value for a function? Gradient, of course, right? So, but of course, if you didn't learn calculus, you are still in the middle school. If somebody asks you this question, you say, okay, I will search the whole interval, right? In that interval, I may take many values. I want to get which value is the smallest one. Now you are a graduate student now, so therefore you say, okay, for those maximum or minimum value, right? Those values will satisfy those requirements that the derivative is 0, right? So the optimal solution should satisfy this condition. Gradient is 0. I think everybody knows this, right? Everybody knows. But how did we derive this condition? We want to be very clear about how we derive this such that we can use the same idea, similar idea to solve the problem we are facing now. You say, okay, you can say, visually, right? Visually, those points are where the derivative is 0. But visualization can help us to think. But visualization, right, is not the proof. So let's try to prove that. Then we have to ask the basic question. When we say a function have a minimum value, what does that mean? The value compared to all the other points, the value must be the smallest one, right? That's the meaning of a minimum value. So let's say if x naught, right, is the minimum solution, then its value, function value f(x naught) must be the smallest compared to all the points around it. Hence, we have to evaluate the change of the function, right, in the neighborhood of the optimal solution and verify indeed, right, it is satisfy this condition. So we take the problem as solved and assume that x naught is the optimal point. Then we need to compute the variation of the function values in the neighborhood of x0. So we want to compute f at the value of x0 plus delta x. Now here becomes a mathematical question, right? If you know a function, how do we evaluate a function f(x naught) plus delta x around x0? There is a very famous formula for that, right? Taylor series. Taylor series is the most important formula in calculus. Okay, now you say, okay, from Taylor series, right, I can expand, I can express the f(x naught) plus delta x, right, as the value of f(x naught) plus the derivative times first order derivative times delta x plus the second order derivative times delta x squared over 2. And of course, there may some other higher order terms. Okay, remember, right? Remember, if you look at this form, right? If x naught is the minimum point, right? Then this fx0 must be smaller than f(x naught) plus delta x for any delta x, or in the neighborhood of this x0. Now, if you look at this expression, it should be clear if x0 is the optimal point, then this first order derivative must be 0. Is that clear? How do we prove that? If this guy is not 0, right? Let's say I want to say this is the minimum value. Then For any delta x, this has to be smaller, has to be bigger than equal to, right? If this guy is not 0, can I choose delta x to make this smaller than fx naught? Of course, right? I can choose this delta x as this, minus this one. That will give you a negative number. We'll make it even smaller, right? In the same way, if we want to show this is the maximum one, right? This also has to be 0, right? This has also to be 0. Okay, so now you can say the first order derivative has to be 0. And also, but then how about the second order derivative? The second order derivative will decide whether this point is a minimum point or a maximum point. If this is 0, then if I want to make this one to be a minimum point, what's the requirement on the second order derivative? Supposed to be positive or negative? If I want to make this to be minimum, the second order derivative has to be positive. Now, everything is clear if you look at the Tanner series, right? Of course, from the Tanner series, you can find out the condition. If both first order and the second order derivative are 0, then what's the requirement on the third order derivative? Has it to be 0? Yes or no? If this is 0, and if this is 0, I also want to, if x naught is the minimum value, what's the condition on the third order derivative? Is it required to be 0? Of course. You will follow the same argument. If it is not 0, you can always find the delta x to make it smaller than fx0. Okay? But the fourth order derivative, that will decide whether it's a minimum. So you can see, that's what I'm saying, right? Don't just remember the condition. So you have to know how to show that, and how to show that is just from the Tanner series. Okay? You can easily prove that. Any questions? All right, so therefore we have to find a way to evaluate this. From this one, we can derive the condition, right? For the optimal condition is that the derivative, this first order derivative, has to be 0. Of course, we know that if it's a minimum value, then whether it's a minimum or maximum, it requires condition on the second order derivative. But for today's class, right, we will not dig into details about that, so we just focus on the first order derivative. Now recall our problem, right? Our problem, of course, is not try to find out a minimum or maximum value for a scalar function, which that one you have already know how to do that. For this case, we have a integral. What is the input to this integral? The input to this integral, right, you can say the functions, right? If you know the function of this y and u, then the integral will be a value, a real value, right? So therefore, this is a map from the space of functions to real number. In the past, normally, right, you have in calculus, you have studied the function, right, which the variable of a function is could be a vector, right? Many variables, or could be one variable, just one scalar. But for this one, the input, right, or the variable of that function is no longer just a vector, is a function. If you put in one function, then it gives you a number. Is that clear? So this is not a simple function, right? We call it functional, right? We have a name for that. Functional in English. Okay, in Chinese we call 泛函. But don't worry if you have not learned, the functional in the past. Okay, so but you have to know there is a difference. There is a difference. So where do we search? So where do we search for the optimal solution for this problem? We are going to search the best candidate in the space of functions, right, instead of variable in a real line, like our f of x, right? So, but now we want to search the whole space, right, of functions. In that case, can we directly use the standard way, right, taking the derivative, making it to be 0 to solve this problem? You don't know how to do that, right? So what is the derivative? Here, the variable is a function. There is no easy way, a direct way to take the derivative and to do it like this. So therefore, this is the subject of what we call the calculus of variations, so which you are going to learn today. Of course, the calculus of variations, that's a big subject. Normally, in math, it may be one course. So that's why we only touch upon the basic idea. And this one, the calculus of variations, it has a long history, and many mathematicians have made contributions to this subject. I will just list some of the very well-known ones, which like Fermat, Bernoulli brothers, Euler, Lagrange, Legendre, of course, Newton and Leibniz, Gauss, Poisson, Jacobi, Cauchy, Weierstrass, and also the other ones, more recent ones. You can say almost all the famous mathematicians made contributions to this subject. And in the history of calculus variations, the most famous problem is this. We call how do we construct a curve of fastest descent? It's a problem from physics. I want to build a surface such that the ball rolling from the top to the bottom, but I want to build a surface in such a way that the time it takes is minimal from one point to another. You say that's a physics problem, but how do you solve it? We need the help from the mathematician. It turns out you should follow this red curve. So you have to go down first and then go up, right? Follow the smooth curve. That one will reach it. That will take the minimum time. You cannot go just draw a straight line. Okay. You also cannot go like this, as you can see. Okay. But of course, today we are not going to solve this problem. It's a bit more involved, but then this is the question, right? I mean, then you want to minimize the time, okay? And then you want to find out a function to do it. So therefore, it's a calculus of variation problem. So interestingly, right, the solution is that you need to overshoot, to be the quickest one. That is kind of against the intuition. Let's go back to our optimal control problem. So we want to minimize this. We want to minimize the value of the output, right? And also want to minimize the average value of the input. We will start with our simplest case, right? Because today we just want to get the solution such that you have a sense about how to solve it. Let's simplify the problem. The simplest system, right, is the integrator, right? Y dot equals U, integrator. There is an initial condition. So Y0, you know the initial condition. For this problem, right, the initial condition should not be 0, right? If the initial condition is 0, the solution is very simple. No need to do anything. the minimum value will be 0, right? You just let u equal 0, and then they will stay there. Of course, this one is not 0. How do we make this integral to be minimized? So this one, we don't need the y dot because u is y dot, right? So therefore, we just minimize the integral of y squared plus u squared. But u is y dot, so it's y squared plus y dot squared. Therefore, that's a very specific problem of a minimization. Okay, so what we want is we want to find a function, right? Y, which is a function of time, is a smooth function such that this integral is minimized. There are many functions, right? How are we going to find it out? Once again, right, this initial condition CR is not 0 because if it's 0, you have a very trivial solution, okay, which you make this y equals 0. Then it solves the problem. But so in the next, we are going to find out a way to solve this problem. So we want to find out a function of time to minimize this functional, where you know the initial condition. Any questions? How do we deal with minimization of a functional? Then we recall what we did, right? Try to find out the minimization of a function. We use the Tanner series because we want to compute the variations of a function around the optimal point. Through this way, right? Through this way, we find out an equation. We find out the equation for that optimal point. Similarly, we first need to know how to compute the variations of functional in the neighborhood of the optimal solution. Once again, so let's take the problem as solved. Let's assume that I already know y naught is the optimal solution. Then how do we compute the change of a function around a point x naught? We use the Tanner series, right? We say, okay, we evaluate a small change about this optimal solution, then use Tanner series, we found this one. Okay, from this expression, we say, okay, this one has to be, derivative has to be 0, right? We derive an equation for that. So in that process, we need to know how the function changes in the neighborhood of x0. Right? Similarly, we need to find out a way to compute the change of the functional around the optimal solution. Why not? So how does this value change? This integral will change when this optimal solution is modified by delta y. Then the question is, how do we express the change of a function, right? The change of function delta y. Let's say this is the function of y, right? Then I can change it, right? You can say I change it to another function, right? I will change it to another function. You can say, how many ways can you change the function? Infinite number of ways, right? Infinite number of ways. That is different from the way, or how we going to change the optimal solution for one scalar function. There is only one way, right? You change x, you change it by a delta x. Infinite number of ways to vary the function. Remember, right, in the one, in a scalar function, there is only one way, right? We put those, because this is a scalar, right? You can only change by a value, one direction, but we use the delta x, right? Delta x to indicate the size of that change, but there is only one way. But here there are infinite number of ways, then which direction to choose. We know there are infinite number of directions to choose, to consider in the functional space. Among all the directions, is there a special direction which is more informative than the others? There are infinite possibilities to change. Is there anything special about one of them? You only, okay, the student said linear function. But remember the solution, right? The solution may not be linear at all. You expect a solution which actually may not be a simple linear function. So therefore, for this problem, of course, we should not give a special position for the linear function. So actually the answer is no. We have to consider all the directions, right? We need to consider all the directions. Therefore, none of the direction is more important than the rest. We have to consider all of them. Okay, so how do we do that? Then we say, okay, look, I just take any direction, so which means, because we're talking about a change of function, which means I'm taking any continuous function, z of x. Then, so we say, okay, I'm going to change, right? I'm going to change my yx along this direction, which means I'm going to compute the change of function in this way. The delta y is just epsilon times z. Z is any function, right? That is the direction you are looking at. Of course, I need to have a epsilon to control the size of the change. It's like in the x0 plus delta x will control the size of the change, right? So let's say this yx is the function, right? I want to change it, and then epsilon will control the size. Here, right, epsilon is small. It's a small change from the original one. If epsilon is big, right, then I have a bigger change. So we introduce epsilon as a scalar parameter to control the size of the change. Actually, which is also true for the function of one variable, right? We use delta x, so epsilon is like delta x. But in that one, there is no z, right? Because there is only one direction we move in. So that z is kind of a constant. Any questions? This is the most important step in understanding the rest of the theory, okay? How are we going to express the change of function delta y? So we express delta y as the size of the change times how are we going to change, which I can change any direction. So I use an arbitral function zx to represent any direction. So zx can be any function or arbitral continuous function. Okay? Any questions up to this point? Like I said, right, I mean, this is the key step. If you understand this, the rest are kind of a standard procedure. We just use our whatever you have learned, what you have learned in calculus. Let's move on. Remember, right, we use the delta y because we want to compute the variation of the functional in the neighborhood of optimal solution. The optimal solution is a function, right? Y out, no? And then we say along a direction, but that direction you can choose any direction z. Therefore, we already expressed delta y as epsilon times z. So we just need to compute this, right? How will this value, right, this integral will change if I change the y naught, right, by this in this direction. Right? So y naught plus epsilon z, then we just plug it in into the expression of the integral, right? We say the integral is this one, the y right now is y naught plus epsilon, right? The y dot, the derivative is y naught dot plus epsilon z dot square. Okay? Straightforward, right? But remember, we already know, okay, in this expression, we say, okay, y naught is the optimal solution. We assume that, okay, I already found it. It's fixed. Then how about this z? We say z is a direction I want to check. But that direction, right, if I pick that direction, I also fix that direction. So z also is fixed. If I give an integral like this, y naught is fixed, z is also fixed, right? Then you have one variable epsilon, right? Then this one, if y naught and z are not fixed, we say is a functional, right? We map from functions to a value. But here, the y naught and z are already fixed. Is it still a functional or it becomes a function? Becomes a functional. That's also a very important step. I fix the function, then the unknown variable is epsilon, right? So it is a function of one scalar variable, epsilon. Is that clear? So look at this expression. This cost, we already changed, right? We say, okay, I will fix my y naught and z, then it is a function of epsilon, okay? It's a function of one scalar variable. Epsilon is the size of the change of the optimal solution. Then, if it just becomes a function of one variable, then the question is simple now. We just need to answer this question. Does this function of epsilon have a minimum value? If it has, where is the minimum value? It is a function of epsilon. Does it have a minimum? Look at that. We know that y naught is the minimum solution, right? So does this have a minimum? It has. Where is the minimum value? Epsilon equals 0. Epsilon equals 0 is the minimum point. Is that clear? Because when epsilon is 0, this has the minimum value because y naught is the minimum solution to that integral, right? For any non-zero epsilon, it is not y naught, right? So therefore, the value will be bigger, okay? So therefore, from this one, if y naught is indeed the function that gives you the absolute minimum of j, then this one, as a function of the scalar epsilon, must have a minimum at epsilon equals 0. Is that clear? Now, if that's the case, we can just use, right, what we have learned from calculus to derive the optimality equation. Okay? So any questions? Then you can say, right, the magic, using this delta y equals epsilon z, we change the problem into the minimization of a scalar function. But how do we minimize the scalar function? That's what you already learned, right? What is the necessary condition of a scalar function? Remember, this is a scalar function. Y naught is there fixed, is a function of epsilon. What is the condition for a function of one variable to have a minimum? And how do we get that minimum? What's the condition? Derivative has to be 0, right? Easy. So it's a function, then the derivative with that variable epsilon has to be 0, and also we know at which value epsilon equals 0. At that point, it should be 0. Okay? Any questions? All right. Then we just need to compute this, right? How to evaluate this? So we already have the expression of this j, right? And we just take the derivative with respect to epsilon. So we first group them, right? I mean, we know, okay, this is a quadratic one. Then we have this one term, right, which is not related to epsilon. And then we have the first order term for the epsilon, and then we have a quadratic term for the epsilon. So it's a quadratic function of epsilon. Remember, y naught is there? Okay, those are the fixed ones. Then we take the derivative of this one with respect to epsilon. So the derivative of the first term should be 0, right? The derivative of the second term, 2 times this integral, right? The derivative of the last term, we say, okay, is 2 epsilon times this one. But remember, we also put epsilon equals 0, right? When epsilon equals 0, this derivative should be 0. So therefore, we can easily obtain that we are left, okay, this one will be 0, because the derivative of this one, when epsilon equals 0, will be 0. Therefore, we have this one. Okay? Any questions? Now we have an equation for this y naught, right? But this equation, of course, is the equation in terms of an integral. We still have to reduce it, right, to some equation that we know how to solve it. Okay, here, this is the equation we're going to deal with. In the next, we want to do some manipulation. We want to change the form of this integral. Because here we have a z dot in the integrand. Here we have z. If both integrands contain z, then it's easy to proceed next. So we have to do something on this integral about this z dot. How are we going to deal with that? Then it is a mathematical problem. Can we change those integral which involve z dot into a form like an integral which only involves z? You learned that in calculus. What is the technique? There is a well-known way to do it, right? If you have an integral with z dot, actually I want to make it into an integral of z. I know probably it's hard for you to, you know it in Chinese, right? You know that, okay, it's called the integration by parts, Or in Chinese we call 分布积分. Basically, the idea of integral by parts is easy. It's about the product rule for the derivative, right? If I want to compute the product of two functions, the derivative of product, we say, okay, I just do it one by one. I do the first one, I do the second one, plus the derivative of the second one, and so on. That's the way, right? That's the way. Then we say, okay, this is the case. we want to show this formula, right? We just take we do the integral on both sides, then we get this formula. Then from this one we know, okay, immediately we know, okay, so therefore, this f times the derivative g, right, of g, this integral equals this one, this integral, minus the integral of f, the derivative of f, right, f prime times g. But what is this integral? Because it's already a derivative of this function. Of that integral, of course, it is the function itself, right? That integral evaluate from 0 to t minus this one. So that is the formula for the integration by parts. Here I just show you how to understand this formula. Okay, now we want to apply the formula to this one, right? Remember, what we want to change this z dot into z, which means here, when we apply this formula, which one corresponds to z? Z corresponds to g, right? And the y naught dot corresponds to f. So therefore, y naught dot corresponds f times g are y naught z. The value are from 0 to t minus, right? This one is f dot, right? Is just y naught dot is f. I have to take another derivative, so it's y double dot times now g is z now. Okay, so we need to, right? Because we want to deal with both terms, they have different, right? They have different. I want to make them contain the same component z, so that's why I need to do this. And we use a well-known trick. We calculate integral by parts. Any questions? All right, we are close. We are close to the final solution. So here is where we are. So integral by parts, right? We obtain, right? We get this expression. Let's look at all the terms. Let's first look at the boundary conditions. What is z, the function of z at t equals 0? Remember, so when we change, right, let's say I want to change the function, right, into another way, right, by arbitrary one, but also we know that any function should satisfy after the change, it should still satisfy the boundary condition because all the candidates should satisfy the boundary condition, right? So I change it. If that is still the candidate, it should satisfy. So which means those y naught plus epsilon z should satisfy the initial condition. Clearly from this one, and we know the initial condition is that y naught is at 0 is c, right? So what is the condition on z at 0? Should be 0. Has to be 0. Okay? Now, but here, how about the value z at t? Can we use the same way to show that z of t is also 0? If we know if we have a, let's say, if we will have a condition of y naught at t equals 0, we can use the same way to show that, right? Okay, not at 0. If we know the y naught at t, right, at t is a fixed value, then we can do it. But in the original statement, we only know the initial point, right? We didn't put any condition on the final point. So we didn't put any condition on the final point, but what is the condition should we put, right? So here is where we are, integral by parts. We get this one, because 0 is 0, so we end up with this one. And also I want to put this one to be 0. I want to put this one to be 0, such that we will have a nice equation. And we know we should not put a condition on z of t. Then we just put a condition on this one, y dot at t. Therefore, let's just assume y dot at t equals 0, such that this term will also disappear. Okay? If this is 0, so therefore we'll have this one. Okay, now, so we have our integral. Now, we say, but this is still a function in a form of our integral. We want to reduce it one more step. Since this equation holds for any admissible function, remember now we say, okay, z is one direction, right? Z is a one direction, and then this one should be 0. But also we mentioned that z can be any direction. So z is an arbitrary function. Now, mathematically, let's say let's look at it in this way. Then I'll do the integral. If I know the gx can be arbitrary, can be any function. So if that's the case, gx can be any function, which can make this integral to be 0. Can you conclude that f has to be 0? Is that obvious? Remember, if gx can be any function, I can put gx equals f of x, right? Then this one, you take the summation of f squared. You put this as 0. If you sum up the value over the whole integral and all the values are positive, and then the summation is 0, what does that tell you? Then all the values have to be 0, right? Does that make sense? Of course, this is not a rigorous proof, but the idea is like that, because g can be arbitrary function. In this way, if you look at this one, this integral is a function times another function, right? This one is another function. But they can be arbitrary. Then this function has to be 0. Okay? Is that clear? Any questions? So finally, we have shown that the optimal solution y not has to satisfy this equation. But look at this equation. Do you know how to solve this equation? That is just a simple ordinary differential equation, and also it is a linear equation, right? This is the famous Euler equation. Actually has a very famous name. You can know, of course, it is originated from Euler, okay? Anyway, so the whole idea, right, how did we derive this? So we try to evaluate, it's the same story as how we try to find out the solution for one scalar function. Right, that one we want to evaluate the change of the function around the optimal point. Then we end up with algebraic equation, right? The derivative has to be 0. This one, we know that the solution itself is not a point, right? It's not a point. It's a function. So therefore, the equation cannot be a simple algebraic equation. We're looking for a function. That's why finally we end up with an equation which is a differential equation. Okay? So in the next I'm going to show you how to solve this differential equation. But before that, let's just take a break. Let's have a 15 minutes break. Then we will continue how do we solve this problem. Right, so I just mentioned, right, fx simple function do this. This one is just now now it becomes a problem of a differential equation. Okay. Welcome back. So let's start the second half. So now we in the first half we derived the Euler equation. Right. Now let's try to solve this. So we say that the optimal solution should satisfy this equation. Okay, and how to solve the ordinary differential equation? Okay, what's the powerful tool? He said, okay, Laplace transform. Right, Laplace transform. Are you taking another course? Are you taking the other course of mine? You know how to solve this. Other students who are taking the EE5103, right, you know, Laplace transform. It's a very powerful, right? Actually, we can't try the famous Laplace transform. We do Laplace transform, remember now we have to take care of the initial condition, right? So because there's a y double dot, so Laplace transform becomes s squared. But then, because y double dot, so we have to consider there are two initial conditions, y not 0 and y dot, so minus s times y0 minus y dot 0 minus y0, right, equals 0. Then we can get the solution in the S domain, right? And of course, at here, that you know, you just do the partial fraction, you can get the solution. Well, the only question is, do we know the initial conditions? Y not at 0 and y dot at 0. What is the condition? Do we know? We only know y not 0, right? We don't know y dot at 0, but we know the y dot at t. So actually, the solution satisfies a two-point boundary condition instead of our initial conditions. So this is where we are. When we use the Laplace transform, we have a problem, right? We have a problem. But can we still proceed with this method? Can we still use the Laplace transform? Even though we don't know the value of y dot 0. He shakes his head. How about others? Is this a dead end? This, you can still carry on, right? Actually, we can. Although we don't know y dot 0, well, we can still assume that, we know, therefore we just put this y dot 0 as a parameter. We don't know the value, fine. We can still get the solution that assumes that y dot 0 is given. Then the final solution will depend upon the parameter, y dot 0, right? We can still have a solution. That solution depends upon what the y dot 0. Then, after we get the form of the solution, how do we find out this parameter, y dot 0? We have this condition, right? We can use that condition to find it out, right? We can use this boundary condition to find out the parameter. That is one way. That is, we can still use the Laplace transform. Here's the magic tool. You can get the solution, okay? But today we are not going to use the Laplace transform. We use a more general way to do it. right? If you don't know Laplace transform, right, you will know, okay, we can solve it without using Laplace transform, okay. Then you need to know some of the theory about how to solve the ordinary differential equation for linear equations. So this is the equation we're facing. This is a linear equation. It satisfies two conditions. From the linear ordinary differential equation theory, we know that we should first get the roots of the characteristic equation associated with this ODE, which is just this lambda squared minus 1 equals 0. This is the characteristic equation for this one. Essentially, right, you put this double dot right, as a square, and the minus 1, okay, there are two roots, 1 and minus 1. Then there are fundamental solutions in this form, exponential form. Of course, like I said, this is from the ordinary differential equation, or ordinary differential linear equation. From that theory, we know this is the way we solve it, right? Then there are two fundamental solutions, e to the power of t and e to the minus t. Then the general solution of those Euler equation will be linear combination of those two fundamental solutions. Okay? Okay, once we are here, then we know how we're going to find out the two coefficients. We have the two conditions, right? So using the two boundary conditions, we will have two equations. Okay, if you put t equals 0, that should be equals t, right? Equals c. C1 plus C2 equals c. The second one, we take the derivative of this one, we get C1 et plus minus C2 e to the minus t, right? The derivative. And then we put t equals t, so we get C1 et minus C2 e to the minus t. This corresponds to this second condition. Is that clear? Then we have two equations for C1 and C2. Easily you can get those solutions for C1 and C2. So I will skip the details, right? You can do that by yourself. Finally, we will have a solution of this output y. This function y is a function of time. Of course, it also depends upon t, depends upon the initial condition. This is in a very interesting form. And we can also put it into another way. This is the hyperbolic, if we use the hyperbolic cosine function, so SH, cosine hyperbolic cosine function, right? If we define, because this one defined as the et plus e to the minus t over 2, right? If we use this notation, we can put the function in this form. Then actually that is the solution to minimize this functional with the initial condition C turns out to be in this way. Is a hyperbolic cosine function. Right? So what does it look like? Here I just show a graph of one example. We say equals the initial condition is 1, and there is the time step, right, is 2. Interestingly, you can say, okay, it's kind of an exponentially decay, right? It's exponentially decay. That is because of this hyperbolic tangent function. And remember, what's the objective? So among all the functions of the time, this is the function which will minimize this integral. So we will put the average of the square of those two values, the smallest. If you look at this, we know it has to be smooth, right? You will say, okay, if I want to make this one, because let's say if you only consider this one, I should make this one drop to 0 very fast, right? That will make the average to be very, but the problem is that if you do that, That will make this derivative to be very big, right? Because we have the requirement, this derivative, the change of this function cannot be too large. Therefore, it has to smoothly decay. But also, it will not decay to zero. Instead, it decay to some non-zero value. Well, that is because of this way, right? We require to be the terminal condition, right? The final step is 2, and also the initial value is 1, so it has to be in this form. A very special case, if the C equals 0, if C equals 0, actually this one also consider the case when C equals 0. We know that when the initial condition is 0, of course, is a very trivial solution, y equals 0, right? This is also expressed by this function, okay? The reason, right, for it not can go to 0 very fast, because we have to minimize the speed of the change. All right, so let's look at a very special case. When the time duration t goes to infinity, because we are normally interested in the case where in the steady state, right? At the steady state, what is the final form? So we know this is the optimal solution of the y. And what is the control input? Input is just the derivative of y, right? We can compute that. This is easy, just the derivative of exponential function. For control problem, we are interested in the case where capital T goes to infinity, right? We want to know not just a finite time, once, okay, as time goes on, what would happen? This way, we just compute. When t goes to infinity, capital T goes to infinity. Okay, we change this one to this form, just divided both numerator, denominator by e to the t, right? That's why I have e to the minus t. But the capital T goes to infinity, right? And also t change from 0 to capital T. Therefore, this term will go to 0, right? E to the minus 2t. That term goes to 0. We only have this e to the minus t. Is that clear? Capital T goes to infinity. All right, so then how about the input? Input is the y dot, so we take the y dot of this one, and then we also put this capital T goes to infinity, becomes just minus c e to the minus t. Okay, any questions? But clearly you can see the relation between the u and y. What is the relation between the input and the output? How do you express the input as the function of the output? U equals, look at this. Y is c to e to the minus t. This one is minus c to e to the minus t. U equals minus y, right? Is that, so it becomes clear. Actually, you have the input equals minus y. So the optimal solution, when t goes to infinity, we can show that, right? We can show that this is actually just is this, right? You can say the input depends upon the output. Is this a feedback control? This is a feedback controller, right? We can show that actually is equivalent to a feedback controller. The optimal controller can be expressed in this form of a feedback controller. Of course, when we solve this problem, right, when we solve this problem using the calculus of variations, we just solve the, this output in terms of a function of time. The input is also a function of time, right? But eventually, those two are related by a very simple form. Now, let's summarize. Right? For this case, we have to show that if we want to find out the solution, if it's a solution is in a space of functions, and we want to solve the optimization problem, so normally we can rely on this calculus of variations to find the optimal solution. Okay. Here I show you an example to solve the optimal control problem, but there are many other other applications where you can use the calculus of variations to find out a smooth function which will minimize something. In the following, we are going to solve a very element problem in calculus of variations, the minimum curve problem. We will try to find out the shortest path between 2 points. But here is just a shortest path, right, between 2 points. We are given 2 distinct points, A and B. From common sense, it should be the line, right, connecting those 2 points. That's the common sense. Those 2 points, what is the curve which has the shortest distance? Of course, should be the line. Of course, if we express this line equation with those two the boundary conditions, when at xa the value is ya, right, xb's value is yb, then this is the equation. This equation you can verify. When x equals xa, right, you get y. When x equals xa, it will be ya, right? This will be 0. When x equals xb, right, will be y. This one xb, right, will be cancelled out. You get yb minus y, so you will yb. But with the knowledge you have now, but today we'll just show you, right, we can use the calculus of variations. We are going to solve this problem. We're going to prove it. Mathematically, we want to prove it that the line, right, connecting those 2 points actually indeed give you the shortest distance. But first, we have to formulate this problem, right, as an optimization problem. For simplicity, we just assume the curve is given as the graph of a smooth function. Then the length of the curve will be given by the standard arc length integral. If a function, a graph, will compute the length, right, we just sum up all the lengths of the arc. And also, of course, the length of this arc, right, we can approximate it by this Euclidean distance, will be delta square plus delta y square, right, the square root of that. So the arc length, right, we just sum up all the pieces, small pieces, ds. Each one, right, is just ds is just the square root of this delta x squared plus delta y squared expressed in this form. This is just some of the review of the knowledge, right, if learning calculus. So how we get that? So we take this dx out. Then in this square root, we have 1 plus, right, dy over dx squared. That becomes, right, here it becomes the derivative of y squared, right? So it's square root of 1 plus the y dot square. This is the dx. Then becomes the integral, right? Integral of a function of y, the derivative of this function of y, integral over x. So then there is a condition on this y, right? It has satisfied this boundary conditions, right? The beginning, right? Because we say the fixed point, right? From the beginning to the destination, those 2 points are fixed. It means at the beginning, it starts from xa, it ends at xb. The positions are fixed, right? When x equals xa, the y value is fixed. The 2 positions are fixed. So xa from xa ya to xb yb. Then it becomes minimization problem, right? So we want to minimize, right? We want to find out a function, right? This is a functional, right? You can say for any function of y, right, we'll get a value, we'll get a distance. We want to find out a function such that this distance of those 2 points is minimized. This function will satisfy those boundary conditions. So, but now there is a difference, right, between this type of the integral, this type of minimization with the original problem we solved. In the first half, the boundary condition is given at the first value y0, right, at 0, but the second value at the last point is not given. Instead, we pose a condition on the derivative. But here are the boundary conditions are different from the Euler equation. Okay, that's the difference you want to keep in mind, because that will also change the way how you solve it. But then how about the Euler equation, right? It will change to another equation. So that is the way we are going to formulate the problem. How do we find out the shortest path, right, between 2 points? But instead of solving that problem directly, let's find out a solution to a more general form. So that is a very specific one, right? We want to find out our functions to minimize a functional. Here, that functional is given square root of 1 plus the y dot square, right? But here we say, okay, look, let's try to figure out an equation to solve a very general one. We want to find out a function which will minimize a cost function or objective functional. So when we plug in this function, right, this functional will give you a value. It is a functional, it's a map between the space of functions of y of x into a number, right? This integral will just give you, for any function, it give you one number. So it is a functional. This integral is known as the Lagrangian for the variational problem in honor of Lagrange. We usually assume that the Lagrangian, right, in this form, R is a function, x, y, p is a reasonably smooth function of all the 3 arguments. There are 3 arguments. There are x, y, and p. So we use p to represent the derivative of y. This one just to simplify the notation, the derivation of the notation, to simplify the derivation. Right? For example, like I said, the arc length we want to minimize. That one is the square root of 1 plus the y dot square, right? Now, because if we use this form, says the Lagrange of x, y, p is just the square root of 1 plus p squared. Remember, p is the y dot. Okay? Any questions? Then the boundary conditions. For this case, there are 2 boundary conditions. One is at the initial value. The other one is at the destination. So y, because the integral is from a to b. So at the a, the value is given, y of a. At b, the value is fixed at yb. So we want to search for a function which satisfy those 2 conditions such that, right, this integral, right, is minimized. Okay? So this is a more general form, and then we want to find out the solution. We are going to use the way to derive the Euler equation, to derive an equation for this kind of minimization problem. Okay? Any questions? So we are going to follow the same way for solving the optimal control problem. To solve this minimization problem, we need to compute the variations of the functional around the optimal solution, right? And we know, okay, let's say we're given a function yx, we consider a variation of this function in any direction. We put any direction here, we use v of x, right? It's any direction or any arbitrary function. And then also we put a epsilon, right, to control the size of the change. So we change the function from y to y plus epsilon v. This is what we did in the first half. At that time, we use there instead of there, we use v. Just show there's a little bit the difference, but the idea is the same. We want to evaluate how we change the function from one function in the neighborhood of one function. Okay? Then we have to evaluate how the function will change, right? So it evaluated this integral y we use the change of this function y plus epsilon v. If the function has changed, then both the function itself and the integral, right, will change accordingly. The integral will change to y dot plus epsilon v dot, right? Then the integral then becomes, right, x of course does not change. X is the variable of the function of y, right? So y changed to y plus epsilon. This y dot is changed to y dot plus epsilon v dot. Okay? Any questions? Okay, once again, if the y is fixed and the function is fixed, this becomes a function of one variable epsilon, right? So, and we know we should evaluate the derivative of this function, right, with respect to epsilon. Then we need to take the derivative, right, with respect to epsilon. This j, of course, is just the integral of L, right? And because this integral is over x, but epsilon is independent from x, so we just take the epsilon for the integrand directly and do the integration, right? So therefore, in the next, let's try to find out a way to evaluate this derivative of L with respect to epsilon. We know this L is a function of x, y, right, and p. Now this x and y, p is a function of epsilon. Which rule should we use to compute this kind of derivative? Chain rule, yes, right, chain rule. The function fx, capital Fx is a little f of g is a function of x, right? How to compute? So therefore, I take the derivative of f with respect to g times the derivative of g with respect to x. Okay, then let's apply the chain rule, right? Apply the chain rule. Here, we know that this one has three variables, x, y, y dot. X does not depend upon epsilon, right? So therefore, we don't need to take the derivative with respect to x. But those y, we know those y plus epsilon v, right? This y, this term, the second term depend upon epsilon, right? That's why we need to take the derivative of this L with respect to y, the second variable. dl dy times, and this one, the derivative of this second term, right, is v. That takes care of the derivative for the second variable. Then the derivative for the third variable, right? We say this one, of course, also depends upon epsilon. So we derivative of L, right? dl dp, because L is a function of x, y, p, right? So it's the dl dp times the final one, right? Is the derivative with respect to epsilon is just v prime, right? It's a v dot. Is that clear? This is just a simple chain rule. We can compute the derivative of the L with respect to epsilon. Okay? Any questions? So we get the derivative of this integral, right, is the derivative of the integrand, in which we use the chain rule, right? And we have this expression. But here, the first term, right, is related to v. The second term, right, is related to v dot. So once again, we want to change the form of the second term into an integral which only involves v instead of v dot. What should we do? Integration by parts again, right? Integration by parts. We do the integration by parts, okay? Want to change that such that we can combine both terms. All right, so this is where we are. This one, right, with integral by parts. First, the total integral is this one times v, right? Here. V times this one. Derivative dl dp. Okay. Evaluate from a to b. That takes minus, right? Minus the v times the derivative, right? V times the derivative. V times the derivative of this term, dl dp. The derivative is with respect to dx. Those two parts, right, I put this red line. Okay, this one, this corresponds to the result from the integration by parts. This one, direct copy here. Okay? Any questions? If, like I said, right, in this class, you just try to follow all the steps. If you have any questions, you can just start ask me. All right, clear, no questions, then we move on. Integral by parts. Okay, then let's look at the boundary conditions. We know y plus, this is the candidate, right? The candidate function, after the change, they should satisfy the boundary conditions. Because y of a satisfy the boundary conditions, then this v of a should be 0, right? In the same way, we can show that v of b should also be 0. Here, we want to show this total integral right here, right, is 0, because VA and VB will be 0. That's where we use the boundary conditions to show that. Any questions on this one? This is, okay, let's first do the first one. The first one is because the YA plus epsilon VA should satisfy the boundary condition, right? Is a fixed value. But YA itself should be equal to that value. Therefore, VA is 0. In the same way, the YB also has a fixed value, boundary condition. So we show VB is also 0. Then finally, we get this one. The derivative, right, of this J with respect to epsilon equals 0. Any questions? But we know, does the integral have the minimum? Is a function of epsilon. Does it has a minimum? It have a minimum at which value? Epsilon equals 0, right? So set epsilon equals 0, this integral, we know the derivative of this one, of the derivative of this function should be 0. Okay, now it should be clear now. Because V is arbitrary function, right? Any direction. In the same way as how we derive the Euler equation, those integrand here should be 0. Okay? Any questions? That is the famous, we call the Euler-Lagrange equation. The optimal solution to minimize the functional under the boundary conditions, right? The boundary values are fixed. Then it should satisfy our ODE. The derivative of the A raised to y minus this one equals 0. Remember, it looks like this is a partial differential equation, but no, it's not a partial differential equation. It is an ordinary differential equation. Because here, in the definition of this integrand, right, the y is a function of x. There is no, it is this partial derivative, because this error is written as a function of 3 variables, right, x, y, and p. That's why you have this partial derivative. But indeed, it is an ordinary differential equation, because let's say once you take the partial derivative, you still have a function of just x, y, and y dot, right? But x, y, y dot is just y is just a function of x. Okay, so eventually, it is not a partial differential equation. It is just ordinary differential equation. The solution is a function of 1 variable. When we say a partial differential equation, we'll say, okay, if our solution is a function of 2 variables. Okay? Is that clear? So any questions on how we derive this Euler-Lagrange equation? Basically, we follow the same way we did for deriving the Euler equation, right? The key is to express the change of the function, right? As, in the form of epsilon times a direction. Okay, any questions? Then let's move on. So now, let's return to the most elementary problem in the calculus of variations. Finding the curve of shortest length connecting 2 points in the plane. As we just derived earlier, right, such planar geodesics, English, but simply just the point, right, the curve which represents the shortest length, minimize arc length integral in the plane, right, This one is just, well, should be in the Euclidean right? It should be the Euclidean distance, or the straight line connecting 2 points. We show, of course, in some other space, right? Some under other conditions, it may not be a straight line. But in this case, we want to show it's supposed to be a straight line if we define the distance, right? The distance on a plane. Now we want to apply the Euler-Lagrange equation to this problem. So let's see how we're going to apply that. So we say this integral, of course, is a function of x, y, and y dot. Actually, it does not depend on x and y, right? Only depends upon y dot. The corresponding Lagrange is, okay, L of x, y, p. You see, it does not directly depend upon x and y, right? Only depends upon p. Okay, any questions? And then find out the corresponding Euler-Lagrange equation. This is the general form of the Euler-Lagrange equation. Here, L is defined as the square root of 1 plus p squared. Let's just evaluate that. What will be the first term? dl dy? What will be the dl dy? Look at this. Does it depend upon y? No, right? So therefore, dl dy should be 0. Let's first evaluate dl dp. dl dp, this one, dl dp, of course, this one is, you can do it, right? Square root of something. Then becomes, right, you do this, this is 1 over 2 in the exponential, so 1 over 2 minus 1, that give you the in the denominator, right? And then you do the integral of this term, that is, because there is a 1 over 2, and then there is a 2p, 2 and 2 cancel out, you have this p in the numerator. Can you say that? Any questions? Okay. So finally, the Euler-Lagrange equation in this case will take this form. So we say, okay, this first term is 0, the derivative, right, dx, this is dl dp is here. And then we can let's do it just slowly. I think this is become the problem in the calculus. How to take the derivative. How do you do this? It involves the multiplication product rule, right? There are different ways how you use the, or you can use the derivative of a fraction. But let's say I think the simpler way you do it with the derivative of a product, apply the product rule. You put it as a product of two functions, right? You do the derivative separately. Let's do the derivative with the first one, right? So therefore, you can say this exponential is minus 1 over 2. That is how we get this minus 1 over 2, right? And this term is 1, this one, because 1 minus 1 over 2 minus 1, that give you the minus 3 over 2, right? But then you apply the chain rule, right? Because this one is a function, right, of y dot. We take the derivative with respect to y dot, right? This is 1 plus the y dot square, so that's how you get the 2y dot. But y dot is also a function of of x. So finally, we have to multiply the y dot, take our derivative with respect to x. Therefore, you have the y double dot. That is the derivative of this first term times the y dot. just have to be, if you have some patience, you do it carefully. You can do it. So I just show you now, because it's a product rule, right? The second term is, okay, I do the integral for this one. This one is trivial, right? Just put this one, keep this term. You do the derivative of second one, that is y double dot. Okay? Okay, and then you do some reorganization, right? You can say, okay, I want to have a common denominator, so I put this one as the common denominator. There is a minus 3 over 2, there is a minus 1 over 2. So therefore, I put this one as the denominator. I put the first one, while the y double dot. Here, those 2 will be cancelled out, right? Then I have this minus y dot square. That is for the first one. For the second one, I have this y double dot, right? I have this one. But here is only minus 1 over 2, right? But here I put those denominator as 3 over 2. So therefore, in the numerator, I should keep 1 plus y dot square over this 1 plus 1 dot square, right, to the power of 3 over 2. That will give you this one, minus 1 over 2. Is that clear? Okay. And this one cancelled out. So essentially we get this. All right. But then with this, what if we know this one has to be 0? What does that mean? If this one is 0, what conclusion can you get? The numerator has to be 0 because the denominator cannot be infinity, right? So only possibility is the second order derivative of y is 0. What does that mean? It means first order derivative is constant. It must be a straight line, right? It must be second order derivative is 0. In that way, you know how to solve that equation, right? You only have the first order derivative. If you think about the Tanner series, right, all the higher order derivative will be 0. So we deduce the solution has to be a linear function, y equals ax plus d. Of course, we know that will describe a straight line. The solution will be a straight line, and also the straight line will, connect those 2 points. So it has to be a straight line connecting 2 points. There is only one line to do that. So in this case, you can say we can use the mathematics to prove kind of a common sense, right? In the past part, you all know, okay, it should be a straight line, but here now you can say, I have more knowledge, I can show that mathematically. So, okay, any questions? All right, let's do a summarize of what we have learned. So the key to the calculus of variations is how do we compute the variations of a functional around the critical point? Let's say why is the optimal solution? How do we evaluate, right, the change of the functional around this optimal solution? The most important trick is to find out a way to specify the change of the function delta y. How do we express the change of the function delta y? You pick any direction, right? and then you put a parameter epsilon to control the size of the change, epsilon times any function. This actually, delta y, for one function, right, with one variable is the same. You have a delta x, x plus delta x, because there is only one way to change, right? So delta x will corresponding to epsilon. Here, you have infinite number of directions. That's why you have to multiply by the in which direction you are looking at for one variable on one direction. Now you have so many directions you have to pick an opposite direction to look. Okay? That's the key technique you should understand in order to solve the calculus of variation problem, right? How do we express the change of the function? Okay? So any direction, right? There can be any admissible function, and we need to introduce an epsilon to control the size of the change, which is the same as for one variable, it's just the delta x. For one variable, what is z? Z equals 1, only one direction. Okay. Then we use, after that, everything else, you just use whatever you have learned, right? That's the way, right? For mathematical problem, eventually, it will go down to, to solving either an algebraic equation, of course, or a differential equation. But eventually, everything goes down to solve an algebraic equation, right? How do you solve the ordinary differential equation? It will pin down to, finally, it will be an algebraic equation you can solve. All right, so that's all for today. And next week, so we will introduce another way to solve this one, which is, of course, kind of more popular. That will be introduction to dynamic programming. Okay, so I will see you next week. Then the PowerPoint slides will be uploaded, right? I mean, all the slides will be uploaded. So you already have my lecture notes. This one, you'll have it.